So the main focus of this section will be multiplicities, talking about the exponents of the x-intercepts of the graph is the basic concept. So let's go ahead and get into this. The first thing we're going to introduce is a fact that says the characteristics of a polynomial's graph are such that it has smooth curves, meaning no pointy edges. So what that means is, think of a parabola. That is what a polynomial's graph looks like. It has a U shape to it. Now, look at the absolute value function that has a pointy edge. This is not a polynomial's graph. From there, it has to be continuous, meaning there are no breaks or gaps. In other words, you can draw it without picking up your pencil. So for instance, if I started drawing something that looked like this, oh, that's a little too pointy. Let me start over. Something that looked like this. This is a polynomial. It doesn't have any pointy edges, and it was drawn in one motion. But if I draw something that looks like this, this is not a polynomial, because even though it doesn't have any pointy edges, notice I had to stop drawing, pick up my pencil essentially, and then start drawing again. That is not continuous, it has a break in it, so we have to say that this is not a polynomial. Okay, so from here, we now introduce a definition that says the zeros of a polynomial function occur when f of x equals 0. In other words, at the x-intercepts. So whenever you hear the term find the zero of a function, it's just another way of saying find the x-intercepts. So let's go ahead and find the zeros of g of x equals x squared times x minus 1 times x plus 2 to the third power. Well, to find the zeros of this, we know that it occurs, a zero occurs, that is, when the function equals 0. So we're going to take x squared times x minus 1 times x plus 2 cubed and set it equal to 0 and solve. Now, whenever something's factored out for us, we know that as long as it's factored out and equal to 0, then we can just set each individual factor equal to 0 and solve. So we get x squared equals 0, x minus 1 equals 0, and x plus 2 to the third power equals 0. And solving for each of these x's, in the first case we could take the square root of each side, which gives us x is equal to plus or minus the square root of 0. In the second case, we can just add 1 to each side, which gives us x equals 1. And in the third case, we can take the cube root of each side, which gives us x plus 2 equals the cube root of 0. We don't need a plus or minus because it is an odd radical. Okay, so continuing on from here, plus or minus the square root of 0, that's just 0. The square root of 0 is 0, and whether you put a plus or minus in front of it, it's still just 0. And then x equals 1 is just that. There's nothing to do with it. And then finally over here, x plus 2 is equal to the cube root of 0. The cube root of 0 is just 0. And subtracting 2 from each side, we get x equals -2. So our zeros are 0, 1, and -2. Okay, so going from here, we can now define the term multiplicity that I brought up earlier. So we say the multiplicity of a zero is how many times the zero's factor occurs in the polynomial. Well, we know that whenever you're talking about something occurring more than once in a polynomial, meaning you're multiplying it out more than once, that's just another way of saying the exponent or the power. For instance, if I have x squared, that just means we have x times x. So that x occurred twice in the polynomial. That's what the multiplicity would be of x. X has a multiplicity of 2 because its 0 occurred twice. So from here, we say that if a 0 with multiplicity, let me start over here. A 0 with odd multiplicity means the graph passes through the x-axis at that value. So this is going to help us figure out how to graph a polynomial based on its zeros and multiplicities. So if a 0 has an odd multiplicity at some x-intercept, let's say we have the following x-intercept right here. If it has an odd multiplicity, let's go ahead and say its multiplicity is 1. So if it were something like x plus 2, just like that in the polynomial, then that means it has an exponent that's technically just 1, so the graph will just pass through this point, like so. A straight line right through it. Okay, now what if we had a multiplicity of 3? Let's say we had x minus 4 to the third power. Now the multiplicity is 3, that's still odd. So let's say we have this x-intercept here with this third power or multiplicity of 3. Well, that means the graph is still going to pass through it, but now it's going to pass through similar to the shape of a graph of x cubed. It's going to look something like this. Notice it's not just a straight line through it, it actually curves through this x-intercept. And this is the case whenever your multiplicity is odd and greater than 1. So this shape that you see here would be the same thing if the multiplicity were 5, 7, 9, and so on. It would get a sharper increase through it as this exponent goes up, but in general, we just typically deal with 1 and 3, as going any higher just ends up giving basically the same shape anyway. From here, a 0 with even multiplicity means the graph bounces back from the x-axis at that value. So let's say, again, if we had x plus 2, but we now had it to the second power. So at this x-intercept, let's say the graph is approaching from the left like this, it would hit the x-intercept and bounce back, similar to a parabola shape. And from there, let's say we had x minus 4 again, but this time to the fourth power. And again, let's say we're approaching from the bottom. Then at this x-intercept, it would begin approaching, and then again it would bounce back down. Again, it would have a sharper increase and decrease. Because the exponent is larger, the increase or decrease would happen much more rapidly. And again, this is why we typically only deal with the graph of, with the multiplicity, that is, of 2. So in general, we're only going to be dealing with multiplicities of 1, 2, and 3, because anything higher will have the same shape, essentially. It'll just look a little bit sharper. Okay, and now finally from here we say that the sum of the multiplicities of a polynomial is the degree. So this is also very useful when we're graphing these polynomials, because if we add up all the multiplicities, so for instance in this previous problem we had, if we add up all of our multiplicities, how we had a 2, a 1, and a 3, that would give us a total of 6. That would mean our degree is 6. So what would that tell us about the graph? It would tell us that the ends of the graph either both go up or they both go down. So this is very useful when we actually start graphing these and we want a complete graph. Okay, so continuing on from here, we have the following example. We want to find the zeros of the polynomial and their multiplicities. Given h of x equals x times 4x squared minus 12x plus 9 times x squared plus 8x plus 16. So the first thing that we have to do to find our zeros is to get this completely factored. Once it's completely factored, we will know what to set equal to 0 and what multiplicities each value has based on its exponent. So, to begin factoring this, we'll start with 4x squared minus 12x plus 9. We need two numbers that multiply to give us 4x squared and two numbers that multiply to give us 9. But then they will add or subtract to give us negative 12x. Whenever you have something that looks like this, generally a quick way you can go about this is to check if it's a perfect square. And we do that by just taking 4x squared and finding its square root. That would be 2x and 2x. And then we take 9 and find its square root. That would be 3 and 3. And in order for this to work out, because this is a positive and this is a negative, this positive tells us both the numbers will have the same sign, and it will be this sign, the negative. So let's do a quick check if this worked out. 2x times 2x is 4x squared. 2x times negative 3 is minus 6x. Negative 3 times 2x is minus 6x. Negative 3 times negative 3 is plus 9. So we get 4x squared minus 12x plus 9. That does check out. That is what we were looking for. And now we can do the same thing with this x squared plus 8x plus 16. This again looks like it could be one of our perfect squares, so we'll take x squared and break it up into x times x. 16 will break it up into 4 times 4. And because this is positive, both of the 4's will have this sign, which is also positive. Let's check if this worked out. X times x is x squared. X times 4 is 4x. 4 times x is 4x. We add those two values together, we get the 8x, so that worked. And then 4 times 4 is 16. So we just did a quick mental math check, and it checked out. So we can now rewrite h of x, which gives us x times 2x minus 3 times 2x minus 3 is 2x minus 3 squared. And then x plus 4 times x plus 4 is x plus 4 squared. So we now can find the zeros and their multiplicities by setting the function equal to 0 and solving. So, starting with the first one, we get x equals 0. The second one, we get 2x minus 3 squared equals 0. And the third one, we have x plus 4 quantity squared equals 0. We'll take the square root of each side in the second and third cases, which gives us x equals 0, 2x minus 3 equals plus or minus the square root of 0, and x plus 4 equals plus or minus the square root of 0. We already know what the square root of 0 is. It's just 0. And plus or minus 0 is still 0. So we get 2x minus 3 equals 0. And x plus 4 equals 0. And now we can solve for each of these. We'll add 3 to each side to get 2x equals 3. And then divide each side by 2 to get x equals 3/2. And over here we'll just subtract 4 from each side to get x equals -4. So we now have all the zeros. X equals -4, 0, and 3/2. And from there, the multiplicities, we can just list beneath them. The multiplicity of -4 is the exponent that was on its factor, meaning this 2 here. Since it was squared, it has a multiplicity of 2. The multiplicity on the 0, again, just the exponent on its factor, which is just a 1. And the multiplicity on 3/2 goes back to this exponent of 2, so it has a multiplicity of 2. And these are all of the zeros of the polynomial with their multiplicities. Okay, continuing on from here, we now want to find the x-intercepts and y-intercept, then give a rough sketch of the graph. So, to find the x-intercepts, those are just the zeros. We're just going to quickly set this graph, set this function that is equal to 0 and solve. Now, one trick you can use when doing this is to note that no matter how many times a factor occurs, meaning no matter what its power is, when you set it equal to 0, you will always end up just having that factor equal to 0. So you can ignore these exponents when you set the function equal to 0, meaning just solve x equals 0, x plus 1 equals 0, and x minus 2 equals 0. When you square root each side, take the fourth root of each side, or the cube root of each side, you will still end up getting 0, because the square root, fourth root, and cube root of 0 are all going to be 0. So, quickly solving for this, we'll go ahead and subtract 1 from each side in the second value to get x equals -1, and we'll add 2 to each side in the third to get x equals 2. Okay, so from here, we now have all of our x-intercepts. To find the y-intercept, that doesn't occur when the function equals 0, but it does occur when we plug 0 into the function for x. So we get 0 squared times 0 plus 1 to the 4th power times 0 minus 2 to the 3rd power. And we could go through multiplying this all out, raising it to the 4th and the 3rd and so on, but notice that we're only multiplying these three factors and one of them is 0. That means the entire result is 0. So for our x-intercepts, we'll go ahead and list these out here. The first x-intercept is 0, comma, remember the y value of your x-intercept will always be 0. The second one is -1, comma, 0. And the third one is 2, comma, 0. As for the y-intercepts, y-intercept, you can only ever have one in a function, sorry. We just found that it is 0, comma, 0. Which makes sense. This x-intercept here is also a y-intercept. Okay, and now with this, above each of these x-intercepts, I'm just going to make note of what its multiplicity is. What the 0's multiplicity is, that should really be said. So this 0, comma, 0 has a multiplicity of 2. -1, comma, 0 has a multiplicity of 4. And 2, comma, 0 has a multiplicity of 3. So this is going to give us essentially everything we need to graph this polynomial. The only thing we should really make note of from here is the degree and the leading coefficient. So let's just quickly note the degree is the sum of all the multiplicities. Remember we introduced that a few moments ago. So 2 plus 4 plus 3 gives us 9. And the lead coefficient well, the lead coefficient is what we get when we take all of the leading x values and multiply them together. So really we should say the lead term. We'll draw the lead coefficient from the lead term is generally the easiest way to do this. So let's go ahead and change this to lead term for the moment. We have x squared times x to the 4th power. If you were to multiply all of this out, the largest term in this part of the polynomial would be x to the 4th. And from there, if you did the same thing here, the largest term in this part of the polynomial would be x to the 3rd. Which gives us x squared times x to the 4th times x to the 3rd is x to the 9th. That's our lead term, which means our lead coefficient is the number in front of it, which is just this 1. And that is the critical thing we need here. The degree already took care of this 9, but we just had to make sure what lead coefficient we had here. You should always make sure to go through it this way, because sometimes you might have something like -x minus 2 to the 3rd power, and that could cause this lead coefficient to be negative, for instance. So make sure you always multiply all of these out when you're finding your lead coefficient. So, what does this tell us about the graph based on this degree of 9 and this lead coefficient of 1? Well, the degree being 9 tells us that the ends of the graph go in opposite directions, and the lead coefficient being 1, meaning it's positive, tells us that the graph will start in the bottom left, and end in the upper right. Remember, if it's negative and the degree is odd, then it would start in the top left and end in the bottom right. From here, we can start putting our x-intercepts and y-intercept in. So the first x-intercept we have is 0, 0. From there, we have -1, 0. And finally, 2, 0. We know that the graph is going to start in the bottom left and then approach this first x-intercept. And when it hits this x-intercept, because the multiplicity is 4, the graph will bounce back. So it's going to look like this. So the graph will start off in the bottom left, hit this x-intercept, and bounce back. But eventually it has to come back to this x-intercept, 0, 0. And because it has an exponent of 2, an even multiplicity, it will also bounce back. So it's going to look something like this. And now from here, the graph has to continue down and then manage to come back to this x-intercept, which has a multiplicity of 3, meaning the graph will pass through this x-intercept with a curve. So it's going to look something like that. So the graph is going to do something like this. It's going to create a valley and then come back up, curve through this x-intercept, and then continue on toward the upper right. This is just a very rough sketch of our graph, but this is all we really need. This gives us a pretty decent idea of what our graph looks like. And this is what we will label f of x. Okay, from here, we now introduce one of the most important theorems in all of mathematics, the intermediate value theorem. The intermediate value theorem says if f of a and f of c, meaning if you take the values x equals a and x equals c and plug them into your function f, if those function values have different signs, meaning one's positive and one's negative, then there exists, this is our there exists symbol, a backwards looking capital E, then there exists a B between A and C such that f of B equals 0. Okay, so let's put this all into more simplified terms. Essentially, if your graph has a negative y value and a positive y value, then at some point between those values, your graph had to hit 0. So, if your graph has a point down here and a point up here, somewhere along the way, it had to cross through an x-intercept. So, let's go ahead and show how useful this is. For this example, we're going to show that h of t equals 7t to the 5th minus 9t to the 4th minus t squared has at least 1 0 between t equals 1 and t equals 2. So how can we show that? Well, if we find h of 1 and h of 2, and they have different signs, then that proves there has to be a value between t equals 1 and t equals 2 that is a 0. Just a note though, if they do not have different signs, if one's positive and one's negative, that does not mean that there is not a 0. It doesn't go backwards. This only can tell us if there is a 0 if we see the different signs, but it can't tell us that there's not a 0, because you could have a graph that looks like this, where you plug in 1 and 2, both of them have negative values, but in between them the graph goes like this. And now suddenly there are 2 zeros between t equals 1 and t equals 2. We don't know for sure. We can only tell if they have opposite signs that for sure there is at least 1 0. So when we plug 1 into this function, we get 7 times 1 to the 5th minus 9 times 1 to the 4th minus 1 squared. And if we go through calculating that really quick, we would get h of 1 equals -3. Now if we plug in h of 2, we get 7 times 2 to the 5th minus 9 times 2 to the 4th minus 2 squared. When we simplify this, we would get 7 times 32 minus 9 times 16 minus 4. At the end of the day, this would end up simplifying to 76. So what does that tell us? Well, between 1 and 2, between t equals 1 and t equals 2, our function goes from a negative value to a positive value. So there exists a 0, there exists at least 1 0 between t equals 1 and t equals 2. Just like we showed here, there could be a lot of zeros between there, but we know for sure that there is at least 1. Okay, continuing on, we now have a fact that given the x-intercepts, which we'll call x sub I, from a polynomial's graph, then we can create a polynomial function by saying y equals a times x minus x sub 1 to the p sub 1 times x minus x sub 2 to the p sub 2 times ... x minus x sub n to the p sub n, such that p sub I is the multiplicity of x sub I, and a is found by plugging in the y-intercept. Okay, this is a very complicated looking fact here, but just the main takeaway. If you can look at a graph and find all of its x-intercepts, plug each of them into this formula. Everywhere you see an x sub 1, x sub 2, x sub 3, all the way to x sub n, that just means all of your x-intercepts. Plug each of them in. Then plug in your multiplicity for each one. So if the graph bounces back, that means you have an even multiplicity. If the graph passes through that x-intercept, you have an odd multiplicity. And remember, we only deal with multiplicities of 1, 2, and 3, because even though, yes, you could have a multiplicity of 17, in general, you're just going to be dealing with 1, 2, and 3 for simplicity. Once you have all of that, just take your y-intercept and plug it in, and that will allow you to solve for any possible a value that could be out here. There could be a random multiple of 3 to all of your factors, so we need to account for that. Doing all of this will allow you to take the graph and convert it into a polynomial. And the last thing to note before we get to this example is that a local or global extremum is a point that rests on a smooth curve such that the local extremum is the highest or lowest point in the specific interval around it. So, for instance, if we have this parabola shape here, this is a local extremum. We call this a local minimum. And then if we have a downward facing parabola, this point here is a local extremum. It is the local maximum. And we say that the global extremum is the highest or lowest point on the entire graph. So a graph can have a lot of local extrema. So here's a local minimum, here's a local max, local min, local max, local min. But if we said what is the global minimum or maximum, then looking at this graph, the lowest point on the entire graph is right here. This is the global minimum. There isn't a global maximum because the graph continues upward forever, so there will never be a highest point on a smoothed curve. Okay, so this is just something to be aware of. With that in mind, let's go ahead and go to this example. We want to find the equation of the graph given below. So, to start off with, we should make a list of all of our x-intercepts and our y-intercept. So starting off, we'll say x equals, going left to right, we have this x-intercept here at x equals -3. We have another one here at x equals -1. Here at x equals 1. And here at x equals 2. So we need to write all of these with their multiplicities. Remember, the multiplicity is very important. That'll tell us the exponent for each of these x-intercepts. So the first one, the graph passes through it very sharply. It's just a straight line through it, which means the multiplicity is just 1. Here, it's kind of hard to tell, but there isn't a very defined curve through it like so. So whenever that's the case, you just want to call it a multiplicity of 1 as well. Unless you can for sure see that curve, then you just want it to be in a multiplicity of 1. Here, the graph bounces back, so it has a multiplicity of 2. Remember, we're not going to put multiplicities of 4, 6, 8, and so on. And finally here, it has another straight line through it, so it's again a multiplicity of 1. I just want to be clear, this one, it is a bit iffy, and I know that's probably a little bit annoying to see. That's not something to really worry about. In general, it's just because this is a terrible sketch on my part. In general, it'll be much more distinctive that it's just straight through or there actually is a curve there. So that's not something to worry too much about. Okay, so now that we have these x-intercepts, let's go ahead and quickly make note of the y-intercept as well. The y-intercept is this point down here, 0, -2. We will need that later when solving for that a value. So, going to our formula, we have f of x equals a times the first x-intercept, so x minus the first x-intercept is -3, to its multiplicity, which is 1, times x minus the second intercept, -1, again to its multiplicity is 1, times x minus +1 to its multiplicity, which is 2, and finally x minus +2 to its multiplicity, which is 1. So simplifying this, we get f of x equals a times x plus 3 times x plus 1 times x minus 1 squared times x minus 2. And we do not have to worry about multiplying all of this out. We can leave it just like this. All we need to do from here is find our a value and the problem's complete. And remember, we find a by plugging in the y-intercept. So we're going to plug in 0 for our x value and -2 for the y value, or the function value. So we get -2 equals a times 0 plus 3 times 0 plus 1 times 0 minus 1 squared times 0 minus 2. And simplifying this, we get -2 equals a times 3 times 1 times 0 minus 1 is -1, squared is +1, times -2. So we have -2 equals a times 3 times 1 times 1 times -2 is -6. And dividing each side by -6, we get 1/3 equals a. So our final answer is f of x equals 1/3 times x plus 3 times x plus 1 times x minus 1 squared times x minus 2. And that is the polynomial function that represents this graph.